So everyone, I hope my screen is visible to all of you. সবাই আমাকে একটু বলে দেবে আমার স্ক্রিন সবার কাছে ভিজিবল আছে আশা করি।
Yes, sir.
So let's start then. এবার শুরু করবার আগে আমাদের কয়েকটা জিনিস এখানে আগে বলে নিই। অ্যাজ ইউজুয়াল যে আমাদের মেজর কনসার্নস যেগুলো থাকছে এই টপিকটার আন্ডারে ডি এন্ড এফ ব্লক এলিমেন্টস, এটার কি কি ফ্লো আমাদের থাকতে পারে চ্যাপ্টার সিনপসিসে। নাও যেহেতু এটা আমাদের ইনঅর্গানিকের টপিকে এনডি এর যে মেন্স বা নিটের মেজরিটি চ্যাপ্টার্স তো আমার রিমুভড, কাজেই লাস্ট 3-4 ইয়ার্স ধরে ডিএনএ ব্লক থেকে একদম এক্সটেন্সিভ কোয়েশ্চেন জিজ্ঞেস করছে। অ্যান্ড ইট ইজ সাচ এ চ্যাপ্টার যেখানে মানে কি বলবো ভীষণ পরিমাণে এনসিআরটি ড্রিভেন কোয়েশ্চেন্স জিজ্ঞাসা করছে। এনসিআরটি খুব ক্লেভার অ্যাজ ইউজুয়াল, একদম কোনো কিছুরই খুব একটা ভালো যে এক্সপ্লেনেশন দিয়েছে তা না, বাট ইয়েস দে হ্যাভ গিভেন এনাফ অফ রিসোর্সেস, so we are supposed to break down those resources and we have to decode them with logic, and we will have to use the concepts of electrochemistry, the concepts of redox reactions in this particular chapter. We have to pay attention towards ionization enthalpy, hydration enthalpy, ionic and atomic radii, stability of oxidation states, and most importantly electronic configuration. তার মানে প্রথম এখানে যেটা আমাদের করতে হবে, তোমাদের মনে করে দেখো আমি বলেছিলাম পিরিয়ডিক ক্লাসিফিকেশন করবার সময় যে তুমি এখন করো কি না করো ক্লাস 12-এ উঠে করতে হবে, মনে আছে স্বর্ণালী? যে আমার ইলেকট্রনিক কনফিগারেশনস এগুলো ক্লাস 12-এ উঠে ডিএনএ ব্লকে করতেই হবে, তাই না? মনে আছে?
হ্যাঁ স্যার।
ইলেকট্রনিক কনফিগারেশনস of M and Mn plus for D and F block elements. এই পার্টিকুলার কনটেক্সটেই আমরা মানে অ্যাটলিস্ট নিটের জন্য একটা কোয়েশ্চেন এক্সপেক্ট করতে পারবো, অ্যান্ড যেই মেন্সে অলমোস্ট অল্টারনেটিভলি সমস্ত শিফটেই একটা করে কোয়েশ্চেন এক্সপেক্ট করা যায় শুধুমাত্র ইলেকট্রনিক কনফিগারেশনস এর উপর বেস করে। দেন সেকেন্ড হচ্ছে অ্যাটমিক অ্যান্ড আয়নিক রেডিয়াই ট্রেন্ডস। মোস্টলি আমরা অ্যাটমিক আয়নিকদের জন্য হরাইজন্টালও দেখব অ্যান্ড ভার্টিক্যালও দেখব। ভার্টিক্যাল যখন দেখবো তখন ল্যান্থোনাইট কন্ট্রাকশন কতটা আসবে অর্ক? কারেক্ট? এনথালপি অফ অ্যাটমাইজেশন, মেল্টিং পয়েন্ট আবার শুরু হয়েছে। melting point and density, most important ionization enthalpy next is oxidation number and their stability, in terms of E naught M2 plus M and E naught M3 plus, মানে আমাদের এখানে রিডাকশন পোটেনশিয়াল দিয়ে আমরা এদের কিছু ডিসকাশনে ঢুকবো। M3 plus M2 plus sixth, oxides, halides and oxoanions, oxocations, oxyhalides of D block, seventh, application, আচ্ছা অ্যাপ্লিকেশনের আগে একটা জিনিস দেখে নেব, that is color of D block cations and their magnetic properties. এখানে শুধু ডি ব্লকই রাখবো না, এখানে আমরা ডি অ্যান্ড এফ কালেক্টিভলি করব। নেক্সট application of transition elements as catalyst and other ninth, chromium and manganese oxoanions, তাদের preparation and properties. That means typically we are now going to study potassium permanganate, potassium dichromate, potassium chromate, their preparation, their chemical reactions. So this will be utilizing the concept of redox reactions. Yes. Before we go for any further context, we will quickly jump into the part of the electronic configuration for transition and inner transition elements. First of all, as I have already forwarded in the group yesterday, that I told you guys to revise and come for the class today with respect of the periodic classification, because periodic classification is going to play a very vital role in this particular first context. So first is the electronic configuration of D and F block elements. Now before we jump into this part and reach any conclusion, let me teach you one interesting thing about which we might have discussed in our 11th preparation of periodic classification, but I told that we will discuss about this later in 12th in details. That is something called, we have studied the Hund's multiplicity law, correct Oshik? We have studied the Hund's multiplicity law. Now how did that Hund's multiplicity law come into the picture? Where did we come to know that, how does it operate and work? That we are trying to understand today first. So origin of Hund's multiplicity law. This thing can be understood. Let's say I am considering dn configuration, some dn configuration, and that we are doing by the idea, Jinia, can you follow? By the idea that there are 5 degenerate orbitals for d subshell. Jinia is there? Mishra?
sir. Yes, sir.
মিশ্র তোদের ইয়ে থেকে কারা কারা আছে মেয়েদের থেকে?
Sir, আছি আমি।
আচ্ছা জিনিয়া থেকে
সবাই তো আছে।
সবাই আছে, গুড। লেটস সে আমি বললাম যেটা একটা D1 কনফিগারেশনকে আমি কনসিডার করছি। নাও অ্যাজ আই টোল্ড দ্যাট each orbital under d subshell is typically characterized by the magnetic quantum number. Each orbital under d subshell is characterized by magnetic quantum number ml. For d subshell, what are the values of ml, guys? Plus minus 2, plus minus 1 and 0, total 5 values. And all these values basically represent degenerate orbitals, correct or not? And what does that mean, degenerate orbitals, Shagorika, Anirban? That means equal energy. Okay, by the way, guys, one small request or disclaimer. We are going to আমরা যদি এটাকে ইংলিশেই কন্টিনিউ করি, কারণ এক দুজন আছে যারা জয়েন করতে পারছে না, মেবি তাদের আমাদের টিপিক্যালি বেঙ্গলি কনভারসেশন একটু পরে গিয়ে এই রেকর্ডেড ভিডিওসগুলো দেখতে অসুবিধা হবে। সো আর ইউ গাইজ কমফর্টেবল ইফ আই কন্ডাক্ট দ্য ক্লাস ইন ইংলিশ অনলি? এভরিবডি?
Yes, sir. Yes, sir.
Okay, great. So equal energy distribution are possible for these 5 degenerate orbitals. If that is true, then there is no specific rigidity that we have to place the electron in the first orbital. It is very much possible for me to place the electron in the second orbital also, or I can place the electron anywhere else. The electrons can be placed anywhere because all the orbitals are degenerate. It is very much unlikely to think that, okay sir, we have seen in many books that the electrons we must start filling up from the left hand side. There is no such rule. There is no such stringent property of filling up orbitals. I can definitely start filling up anywhere else because in the beginning all the orbitals are degenerate. Yes, we have to keep this in mind that when we are going for D2 configuration, then the next electron, the second electron, must be filled up with the parallel spin, with the same spin in the subsequent orbital. But that subsequent orbital does not mean that it has to be the adjacent one. It can be this one also. It can be this one also. Are you guys able to follow? I can place the electrons until and unless I am reaching the half filled state. I can place shuffle the electrons in any possible way. Can you follow, guys?
Yes, sir.
So,
Yes, sir.
so রিক, এটা কি তুই জয়েন করেছিস? চিন্টু জয়েন করেছিস? অনুরাগ চেক আউট, ইজ ইট রিক?
That's a Rick, another Rick.
Okay. While filling up the electrons, we can do so in any orbital, just keeping one thing in mind, that consecutive, that means একের পর এক, পরপর consecutive filling up should occur with parallel spin. Now why is that so? That also we will be explaining. Now this can be understood by the virtue of this can be understood by virtue of exchange energy. What does that mean? The energy additionally released if electron can be rearranged within the degenerate orbital set that means if I can reorganize, if I can shuffle the electrons, unpaired electron in as many possible ways as we can, then it will create an additional stability to the system. That means if there is no such thumb rule, if there is no such boundary that I have to place my electron at this particular orbital, it is very much similar to the concept of resonance. That means if greater amount of delocalization of the electrons among the degenerate set of orbitals is possible, is allowed, then it will, just like resonance, bring more stability to the system. While we were studying this periodic classification back in class 11, we did not have any idea what is called delocalization, what is called resonance, how does the stability factor operate, but now we do. Correct or not, guys? So that's why I am utilizing this term, that if we can unambiguously keep on rearranging the electrons in different orbitals, then I will be able to bring more stability to my system, and therefore it will give me extra benefit, and that benefit is understood. Just like in resonance, we used to call resonance energy, here we are calling it exchange energy. So exchange energy is very much comparable to the idea of resonance energy. Can everyone follow that?
Yes, sir.
So it is comparable to resonance energy.
Sir, স্যার বলছি আমার নামে মিথ্যে একটা রয়েছে, দেখুন তো ওটা এখানে প্রবলেম হচ্ছে।
কি এটা
লেখা আছে অরিত্র TR লেখা আছে লাস্টে, দেখুন
ওটাকে বার করে দিচ্ছি তাহলে।
বার করে দিন ওটাকে, দেখুন চ্যাটে কি লিখছে।
সৈকত একবার চেক করিস যে সৌস্তবটা আমাদের 12 এর সৌস্তব কিনা। So these are the scenario to go for the exchange energy. And how do we find out exchange energy? We will do it this way. E exchange is equals to n into n minus 1 upon 2 k. K is some constant, and you can also derive it on your own. For the engineering aspirants, I am telling, if one particle has to be combined or has to be distributed into two boxes in an unambiguous way, the number of possible way of shuffling that is going to follow this formula NC2. Correct or not, everyone?
Yes, sir. Yes, sir.
So E exchange is directly proportional to NC2, which brings me NC2 multiplied by K, and if I just apply the concept of combination formula, it will give me the idea of n factorial multiplied by n minus, divided by n minus 2 factorial multiplied by 2 factorial into K. Now in the numerator part I can split it further, n into n minus 1 into n minus 2 factorial divided n minus 2 factorial, and 2 factorial as we know 2 only. So these two terms get cancelled and finally we end up getting this expression. Now those who are NEET aspirants need not, tell me?
Sir, can you explain why exchange energy is proportional to then?
Exchange energy is proportional to what?
NC2.
If one particle, let's say for example one electron, I have to distribute in any two unambiguous or any two non-distinguishable orbitals, two non-distinguishable boxes, I have to shuffle one particle, and let's say n number of particles. I have to shuffle n number of particles into two boxes, and the boxes are identical boxes. Then what is the formula of distribution? So that's how we are getting this formula derived. If we do not want to get into the derivation, don't worry, they are never going to ask any numerical on this, but yes, we should know about this one because this is going to play a very vital role very shortly. Now if I want to go for the calculations of several systems, so Dn configuration, if I write down this side, and on the other side I am writing the exchange energy value, it is very much comparable to resonance energy. For any delocalized system, higher is the value of resonance energy, higher is the stability. Similarly, for any Dn configuration, greater is the exchange energy, higher is the stability. Can you follow, guys?
Yes, sir.
So exchange energy needs to be calculated n into n minus 1 upon 2. Obviously, as you can understand, n is the number of electrons. N is the number of electrons with parallel spin. So one by one, if I start counting the thing,
Sir, K key.
some constant, proportionality constant. This is some proportionality constant, proportionality. Clear, everyone? So let's say D1 configuration, that means n value is coming to be 1. So it is 0 K. That means no exchange energy. D2, that means n equals value is 2. So what will I be getting? Calculate, everyone. 2 into 2 minus 1 upon 2 K. That means it is just K. Now D3 configuration, N3. How much is it coming? 3 only. 3K. Now you see, for this 3, if I would have done otherwise, the number of electrons with parallel spin, as we know, we are writing this way. Let's say something like this. Any orbital can be taken up, that's why I am taking it this way. Now, what if I plan to violate the Hund's multiplicity law? What if I plan to violate the Hund's multiplicity law and just for instance I am keeping the third electron with an anti-parallel spin. So with this logic, what am I going to obtain as my exchange energy value? So it is going to give me what you see, 2 electrons with parallel spin. So 2 into 2 minus 1 upon 2k, and the other one is giving me separately and treating that separately, so it is plus 1 into 1 minus 1 by 2k. So if this would have happened, what would have been the ultimate exchange energy value against this D3 configuration? 2k. Now, if I consider D3 configuration like this, as we have been studying since our 11th standard, as we have been writing the D3 configuration since our 11th standard like this, that would have given me the exchange energy value of 3k. But what if I would have violated my the electronic configuration according to Hund's rule, and the third electron by mistake or by some illogical treat, I would have placed my third electron with an anti-parallel spin. Under that scenario, what would have been the value of the exchange energy? Then কত হতো এটার exchange energy? অন্বেষা সাহা, মিশ্র, অর্চিতা, অর্ক, অরুণ, দেবাঙ্গী, if I would have done it the other way, is my voice coming to all of you? Oh my god. Hello? Are you guys able to hear me? এবার শোনা যাচ্ছে? জানি না কেন ইন্টারনেট কানেকশন লস হয়ে গেছিল। জাস্ট মিনিট, আমার এখান থেকে তো রেকর্ডিং এর জন্য এটাই চলে গেছে। Just a minute. Am I now audible? Is my voice coming to all properly?
Yes.
Internet connection disconnect হয়ে গেছিল। So as I was asking that আমরা যেটা করে এসেছি already, আমরা এটা লিখে অভ্যস্ত that T3 configuration used to be written like this, but then we used to give the argument that this configuration is according to Hund's multiplicity law. But where did that Hund multiplicity law come from? It came from the calculation of exchange energy. The basics of Hund's multiplicity law is the exchange energy calculation. Now, according to exchange energy calculation, if someone would have drawn or written the electronic configuration for D3 like this, then the exchange energy would have been how much? Everybody, how much?
2k.
2k. But if according to Hund's multiplicity law, what we used to write the actual electronic configuration against D3, then the actual exchange energy is coming 3k. Now higher is the exchange energy, higher is the stability. That means D3 configuration I should be writing in the first way or in the second way.
First.
Correct. So lower exchange energy implies lesser stability. So this way of writing it is wrong. This is correct. In the similar way, now I ask you guys to quickly complete the exchange energy calculations for the remaining configurations and show it to me. D5, D4, D5, D6, D7, D8, D9, D10. Have you guys understood what am I exactly asking for? যে তোমরা এটাকে ক্যালকুলেট করো, এদের corresponding exchange energy values গুলোকে you calculate the exchange energy values. অনির্বাণ বুঝতে পেরেছিস কি করতে বলছি? अर्क, बुशरा, समझ में आया तेरे को? जैसे हो गया सेंड प्लीज। মারিয়া বুঝতে পেরেছিস কি করতে বলছি? মহসেন বুঝতে পেরেছিস কি করতে বলছি?
মানে নরমাল n/-1/2 এর ফর্মুলা। হ্যাঁ,
বাট যেখানে যেখানে পেয়ারিং আসছে সেটাকে তোমাকে অ্যাডজাস্ট করতে হবে, কারণ প্যারালাল স্পিনের যে কটা n ভ্যালু, মানে এটা যদি d6 হয় n এর ভ্যালু 6 বসালে হবে না, কারণ 5টা ইলেকট্রন প্যারালাল স্পিনে আছে আর একটা উল্টো স্পিনে আছে, তাহলে 5টার জন্য আগে অ্যাড করব প্লাস একটা যোগ করাতে করব। প্রাঞ্জল বুঝতে পেরেছিস? রণবীর, রিমঝিম, সত্যজিৎ, সৌনক, সায়ক, সোহিনী, স্বরূপা, come on, do it and share, come on fast. So against D4 configuration, what is the calculation are we going to get?
6.
So yes, 4 into 4 minus 1 upon 2k, that is Jinya Kuttamachi na 6k. Against 5 into 5 minus 1 by 2k, that is going to come 10k.
10k.
Yes. Now for 6, D6, 5 electrons will be there with parallel spin. No, I cannot do it like that. 5 electrons will be there with parallel and 1 electron with anti-parallel. So for that I have to count separately.
What about 15 years, sir?
No, never. It is coming 10 only. Because this value is 0. This value is 0.
In that way, sir, which you have written in the lesser stability, that will be also only k. Sir, what is k over? Okay over.
স্যার এটা k হচ্ছিল।
কোনটা কি হচ্ছিল?
এটা আপনি লোয়ার
D3 এটা লোয়ার
ও
স্টেবিলিটি।
আচ্ছা, কত আসছে? ও হ্যাঁ, কে আসছে? yes
k
yes correct. Anyway, that is lower stability only, na? So this one, what are we supposed to do? In a similar way, this plus 2 into 2 minus 1 by 2k. So how much is it bringing? 11k it seems. So for D8, this value you see, I will write down the value here over here, it is 10k. So I don't have to write it again and again. So it is 10k plus 3 additional electrons. So against 3k, what we have found, it is 3k against D3. So against 3 unpaired electrons with parallel spin, it will come 3k. So that will give me total 13k. So when I'm going for D9, it is actually D9 can be thought of 5 plus 4. It can be thought of 5 plus 3. It can be thought of 5 plus 2. It can be thought of 5 plus 1, like that. So in that regards, I can write it 10k plus against 4 I have got 6k. So it is 16k. For 10k I can write it 5 plus 5. So 10k plus 10k is 20k. That is the reason you see full filled configurations are maximum stable.
in that way, you can, with the help of each calculation value, so we can also tell that half field stability is lesser than 11K. But sir, that is not true.
No. It is true, because if you guys can recall, আমি বলেছিলাম যে half field configuration stability can be compared with the adjacent configurations. I can compare the D5 stability with D4 and D6. I cannot compare that with D7. But with that regard, if I approach, then someone will come and tell, sir, D5 has 10K, D6 has 10K, then they are comparable stability. How is it true that D6 is lesser stable than D5? Yes, that is true. But you have to understand that when I am going to draw the configuration for D6, then I am going for an additional pairing. Pairing of electron is starting. Due to this pairing of electron in the same orbital, this pairing of electron in same orbital creates repulsion. That is added as a pairing energy. From D6 onwards. Till D5 there is no pairing energy, no repulsion, so only we are considering the exchange energy. But D6, D7, D8, D9, D10, there is an additional repulsive energy getting developed due to the pairing of electrons within the same orbital. So that accounts for little drop in instability. So if I consider D5 with D4, then there is a clear win, because D4 exchange energy হচ্ছে 6K, D5 exchange energy is 10K, so 10K is more stable, D5 is more stable with respect to D4. But what about D6, sir? How do we explain that stability? That can also be understood and explained by the same way, because in D6 as compared to D5, there is an extra electron in the same orbital that causes a bit more repulsion, which decreases the stability overall. So that is the reason D5 is more stable than D6 and D4. But yes, remember, I cannot simply compare the stability of D7 with D5. Why? Because D7 has 13K. That means exchange energy is very high. That can overcome the pairing energy maybe. I don't know. So that is the reason I will not be going for, yes.
স্যার আমরা আগে করেছিলাম যে হাফ ফিল্ড কনফিগারেশন বেশি স্টেবল হয়।
I told you, remember, আরে অর্ধেক জিনিস মনে রাখলে তো মুশকিল, বাকিটা ভুলে গেলে তো মুশকিল। Try to recall. The half field configurations are more stable than its neighboring partially filled configurations. Neighboring, that means I can compare the stability with D5 with D4 and D6, because they are neighboring configurations. I cannot compare D5 with D7, D8, D9. Clear for all?
Yes, sir.
Everybody clear?
Yes, sir.
Yes.
Acha, now you see. Once we have understood this concept of exchange energy, now we are going for the next understanding. You see, very often the energy gap between n-1 d subshell, you think and tell me what is the n plus l value coming out, because n plus l value only decide the energy. So how much is it coming? So it is coming as n-1 as the value of n, and for d what is the value of l? 2, no, everybody?
Yes, sir.
So it is coming n plus 1. So energy gap between n-1 d subshell and ns subshell, for which what is the value of n plus l? Tell me. N value to n only, and for somewhere did we do something wrong? 3D 5. Okay, so it will be how much? N plus 0, n only, correct or not? So n minus d subshell is of very a little amount of higher energy according to Aufbau rule. According to Aufbau rule is very little. As a result, electrons from NS subshell can very often be reshuffled into n-1d subshell to increase the exchange energy in the d orbitals. That is why if you can recall, for writing the electronic configuration of chromium, we used to bring down one electron from 4s to 3d. We used to bring down one electron from 4s to 3d for copper as well, because so that if I do that way, it will increase the exchange energy of the system and it will bring more stability to the system. And why did that happen? Because the energy gap between the n-1d and ns subshell is not very large. As we see in the p block elements, the energy gap between ns and np, they are not very much close. So I just cannot simply shuffle the electrons in between s and p orbital, but the electron energy gap between ns and n-1d subshell, এটা খুবই কাছাকাছি। কাজেই যদি দরকার পড়ে, if it is needed to give a boost to the exchange energy to increase the overall stability to the atom, it might be possible, it may be possible that the electron from ns energy subshell can be brought down to the n-1d subshell. Are you guys able to follow?
Yes, sir.
So what I'm going to do is quickly 3D series, although we have done this in class 11th also, but still we are supposed to do it once again. 3D series, 4D series, up to 5D series will do. Orijit, mute করো।
सर वो तो हमारा अकाउंट ना।
ओह अच्छा।
वो सर हमारी है। इसमें
So 3D series means the first transition series. First transition series, which appears in 4th period. 4D series, that means second transition series. 5D series, that is third transition series. Second transition, third transition series, it is 5th period, it is 6th period. So what were those elements? So the first one was scandium, titanium, it will not be taken. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So if I want to go for the group writing also, এর গ্রুপস গুলো কি কি হবে? It starts from third group, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th. From 13th, P block will again start. Correct everyone? Now down the group if I am moving, scandium, yttrium, lanthanum. बोलते থাকো সবাই. Scandium, yttrium, lanthanum. Then followed by, I told to titanium, zirconium, hafnium. I told you guys to come and revise and come before the class starts. Vanadium, niobium, tantalum. Then chromium, molybdenum, tungsten. Then manganese, technetium, rhenium. Then iron, what is that? Ruthenium, Ginia Blogeli, osmium. Cobalt, rhodium, iridium. Nickel, palladium, platinum. Copper, silver, gold, cadmium, mercury. Now their electronic configurations, we are only writing the electronic configurations against the, what is that called, valence shell, outermost shells, not the kernel ones. I am not showing the kernel ones. So what is it happening here? For scandium I can do it 3D followed by 4s. This is 4D 5s. Then 5D 6s. তোমার যদি মনে থাকে, then lanthanum পর lanthanides started. So actually before hafnium 4f orbital is also filled. এর আগে কি আছে? এর আগে তো ল্যান্থনাইডস গুলো হয়ে গেছে। So before these 4f14 is common. 4f14 I am not writing every time, it is common. It might create confusion, that is the reason I am giving the boundaries. Now if I recall the electronic configurations, from scandium it was 4s2 3d1, or rather 3d1 4s2, 3d2 4s2, 3d3 4s2. For chromium, try to recall guys, it was not 3d4 4s2, it is 3d5 4s1, 3d5 4s2. 6 2 7 2 8 2, then again not 9 2, it is 10 1. To boost the exchange energy, now we can understand, to boost the exchange energy, and it is 10 2. And similarly this is also 10 2, this is also 10 2. For copper and silver and gold, they have the same anomalous electronic configuration, 10 1 10 1 10 1. We have done these things already in 11th standard, and I'm just giving you the quick recap on this. Now, when it comes to 4D series, then there happens the maximum anomaly. That means for yttrium it is 5:4d1. For zinc 5:4d2. Then from niobium onwards, it is always one electron in the s subshell. It was supposed to be 3-2, but it will be 4-1, 5-1, 6-1, 7-1, 8-1. For palladium it is supposed to be 9-1, but it does not. It follows 10-0. Remember everyone? For nickel, palladium, platinum, all used to follow the very much exceptional patterns. When we come to the fifth transition, কোনটাতে টেকনিশিয়ানে কি করেছিলাম আমি
5:45
হ্যাঁ is it so এরকম কিছু বলেছিলাম তাহলে এটা কারেকশন করে নিস কিছু হয়তো বলতে গিয়ে বেরিয়ে গেছে everyone do the correction accordingly then exactly it is for 4D series it does not have any proper explanation. Exchange energy terms so we cannot explain. When it comes to 5D series, now it does not show any anomalous as to some extent. Yes, anomalous in platinum, very much anomalous. It is supposed to be either 8-2 like nickel or palladium like 10-0, but platinum is something different. It is 9-1, and there is no such proper logical explanation against this also. But apart from it, all the other pairs do not show any kind of anomalous pair. That means it is 2-1, 2-2, 2-3. Even tungsten, it is not 1-5, it is 2-4 as it's supposed to be. Then 2-5, 2-6, 2-7, but then it was supposed to be either 2-8 or 10-0 like nickel or palladium respectively, but in platinum it is 1-9. So these are some of my electronic configurations for D transition elements. That is very much useful and important. That is going to play a very vital role very soon when we are going to start discussing the different kind of ionization enthalpy trends and electronic configuration trends. That will play a very vital role. So this is the transition element electronic configuration. Next we are supposed to go for the inner transition, that is lanthanides and actinoids electronic configurations. These are for my transition electronic configurations. Now lanthanide electronic configurations. So as I told you that you can skip for the time being, but in 11th anyway you have to do the electronic configurations as well as the naming for lanthanide elements as well. So lanthanum is not lanthanide, obviously, as I told that time also. Lanthanide starts from atomic number 58, that is cerium. Cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holonium, aerobium, thulium, ytterbium and lutetium. It starts with atomic number 58. Yes, in the examination atomic numbers will be given, but you have to understand the electronic exceptional features of electronic configurations. Atomic number in the exam, it will be provided, but the trick which I am telling, if you can remember that at least, then still without remembering the names in a sequence, we might be able to solve the questions. And it is ending at atomic number 71. Now for all these xenon electronic configuration will be in the kernel. I am skipping those. So it is like to be 5D, outer it is 6S, inner it is 4F. Correct everyone?
Yes, sir.
Yes, sir.
Now let's say so you see, in none of the cases electrons from S, because now the gap between 4F and 6S is very much more higher. So electrons cannot be transferred in between 6S and 4F ever. So it will always be 6S2, 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 2, 2, 2, 2, 2, 2, 2, 2 and 2. Then we will just remember it this way, that lutetium for lutetium, gadolinium and cerium. Only for these three elements alone I will be having electrons in the d subshell. What did I say? Only for these three elements electrons are there in the d subshell. Can you guys follow what I am saying? Then what about others? They do not have electrons in d. Their d electrons has been transferred into where? The same thing as was happening in the d block elements. Electrons were getting transferred from 4s to 3d, 5s to 4d, 6s to 5d. Here it is happening, the electrons are getting transferred from 5d to 4f. Now to enhance the exchange energy in the 4f subshell level. So it will always be, it is first cerium, it is 4f1. Then for praseodymium, it is supposed to be 4f2, 5d1. No, it is not like that. It is 30, 40, 50, 60, 70. Oh, when europium got its half-field stability, this is half-field stability achieved. Then it realized, I should not change my F7 configuration. Let us put my extra electron not in the 4F but in gadolinium, that we will put in the 5D. So in gadolinium the electron is not disturbing, or the electron is not getting into the 4F subshell. It is not disturbing the half-field stability enjoyment for europium, I mean the 4F. It is saying that okay, to some extent jotokkon para jay ekটু to moja kore ni. So 4F is getting the 4F is not getting any electron in gadolinium. The next electron is entering in the 5D. So it is maintaining 4F7. But then again from terbium it started happening the same way. That means it was supposed to be 4F8 5D1. No, it will be 90, 10 0, 11 0, 12 0, 13 0, 14 0. So automatically F subshell fully filled. So the next electron has to enter in the 5d. Are we clear? Tell me, everybody. Come on. Mostly no, but to some extent by exchange energies. ঐশিক তো ফোন আনমিউটেড আছে, কিছু বলবি? হ্যাঁ। Now, are we clear till now, everyone? Now, just a minute. Let's say if I am going to ask for electronic configurations Ln plus 2. हाँ Ln
আগে বলবেন তো
আরে বোঝো আগে দেখে নিস না কেন পুরোটা আগে লিখতে শুরু করে দিস পাগল Ln plus 4. What is Ln, sir? Ln means general representation of lanthanides. Lanthanides is a segment of element that appears post lanthanum. So I am categorizing them, I am giving them a general name defined by Ln. So Ln plus 2, Ln plus 3, Ln plus 4. Can you write down the electronic configurations for these? As we know, the first electron must be lost from the outermost shell. Correct or not, guys? So all I'm asking to do is you write down the electronic configurations after removing the electrons. What am I supposed to expect to get in Ln plus 2, Ln plus 3, Ln plus 4? Can you understand that? Come on, quickly. আমি কি বলতে চাইছি বুঝতে পেরেছি সবাই? আমি বলছি এর থেকে একটা দুটো ইলেকট্রন, তিনটে ইলেকট্রন, চারটে ইলেকট্রন বের করে নেওয়ার পর what will be the remaining configurations? I'm asking you to write down that for each element. Have you understood? Yes or no?
Yes, sir.
Come on, quickly do it, quickly do it. ল্যান্ডস্কেপ করলে ওকে Done. সাগরিকা, ঐশিক, অনির্বাণ, অনুরাগ, অন্বেষা, অর্চিতা, অর্ক, অরুণ, আর্যদীপ, রোশরা, দেবাঙ্গী, ডেকা, সামন্ত, দেবার্ঘ, জিয়ার, লতা, মারিয়া, মৌসম, নেহা, মুকলেশ্বর, প্রিয়াংশু, রিমঝিম, রণবীর, ব্যানার্জি, কিনুরুদ্দিন, সত্যজিৎ, শিবাঙ্গী, শ্যামাশ্রী, সোহিনী, সৌমিক, স্পন্দন, সূচনা। মানে হচ্ছে কি হচ্ছে না এটা? Are you guys able to do it? Everyone?
Yes, sir.
Once we are done with this part, at least there is going to be very high chance that we will be able to solve, or we will be able to get one question for sure in common. For boards examination, 100% you be assured about it that একটা question তোমার আসবেই আসবে, ইলেকট্রনিক কনফিগারেশনের উপরে কনফার্ম আসবে। অরিজিৎ, তোর ইম্পোস্টারটাকে তাড়িয়ে দিয়েছি তো?
হ্যাঁ স্যার, ওটাই ছিল।
Share everyone, share. মিশ্র, শ্যামাশ্রী, মৌসম, শেয়ার করো। করতে পারছি তো, না করতে পারার মতন কিছু তো নেই। What will be for this one? For ln plus 2, if I look at it, it will be 4f1 5d1. Correct or not?
Yes sir.
Correct?
Yes sir.
Now, something I am going to write. Once Mn plus ion gets formed, very often to increase the, we are talking F block elements, right? So we will be concerned about exchange energy for which subshell? D subshell exchange energy I will be favoring, or F subshell exchange energy I will be more bothered.
Yes.
So what I will do is, once it is some plus 2 plus 3 charge, even if D electron is there in the electronic configuration, I will merge that D electron into the F electrons. I will bring down that D electron. Anyway, D electron will only be there for lutetium, gadolinium and cerium. For gadolinium, if I look at it, if you write the electronic configuration for Gd plus 2, it will be how, what is it? 4f7 5d1. So 4f7 is half filled, so we will not break it. But for cerium, it is 4f1. It is 4f1 5d1 for cerium plus 2. So what will I do is, I will transfer this electron into 4f so that 4f can enjoy more exchange energy. Can you follow?
Yes, sir.
Because 4f will have one electron, means exchange energy will be 0. If I can make it 2 electrons, then exchange energy will become 2k. So it will be increased by 2 units. So it will become more stable. So I will make it like, I will write it down. Lata, mute yourself. Once Mn plus ion gets formed, very often to increase the exchange energy stability in the F subshell or for D block elements, I will come on this topic later, for D block elements, or for D block elements, same logic, is applicable with respect to the n-1 D subshell. To increase the exchange energy stability in the F subshell, we bring down the 5d electron into 4f. That is, cerium plus 2, we will not write 4f1 5d1, it is wrong. Cerium plus 2, we will write 4f2 5d0. So it is not correct way of representing. To increase the stability, we will write it in this way: 5f2 4f2 5d0. This is correct. For the later ones, there is already no electron, there are already no electrons in the 5d subshell, so there is no point of confusion. It is simply 4f3, 4f4, 4f5, 4f6, 4f7. But for gadolinium, should I bring down the electron from 5d to 4f? Orko? It is already half-fill stable. Why am I going to disturb the stability by bringing down the electron from 5d to 4f? Urchita, can you follow, ma?
Yes.
So, for gadolinium plus 2, it is already 4f7 half filled stabilized. So we need not to disturb its stability by further bringing an electron from 5d to 4f. Then again thereafter, what are we getting? 4f9, 4f10, 4f11, 4f12, 4f13, 4f14. Now once 4f14 is fully filled, then we do not have any other choice of bringing down or something like that in lutetium plus 2. So it will be 4f14 5d1. Clear? So only for cerium plus 2, I will bring down my electron from 5d to 4f to account for greater exchange energy stability. Clear for everybody?
Yes, sir.
And now obviously when we are now going for the Ln plus 3 configurations, there will not be any other d electrons left. I will have to release the electron from F subshell only. So what am I supposed to do? Simply we will change. It is 4F1, 4F2, 4F3, 4F4, 4F5, 4F6, 4F7, 4F8, 4F9, 4F10, 4F11, 4F13, 12, 4F13 and 4F14. Clear for all?
Yes, sir.
Now when we come to talk about Ln plus 4, now all the elements will not have their plus 4 oxidation states. Yes, I can definitely go for writing the different electronic configuration against plus 4 oxidation state, no problem. But all will not have their plus 4 oxidation state in existence. Only 5 elements I will be making their existence in plus 4 oxidation states. Can you guess at least one example where definitely plus 4 will be existing? Can you guess any element from these where plus 4 oxidation state will definitely exist?
Cerium.
Huh?
Cerium.
Okay.
Sir, TB.
TB, yes. As you can see, in TB plus 3, it is D8 F8 configuration. If I somehow remove another electron, it will become F7 configuration. Can you follow that? Everyone?
Yes, sir.
So if I remove this electron, it will convert into 4F7, half filled. In the beginning, Ornish told one very clear good thing that sir, cerium plus 4 can also exist. What is the logic? Because for cerium plus 4, if you look at it, it will get the xenon configuration. If I make it 4F0, then it will become inert gas configuration. It will get inert gas configuration. Am I clear for all or not?
Sir, but the excitability is more.
Correct. But inert gas configuration stability is very high stability. Ionization energy will be low. It will be easy for us to remove the electron. Inert gas configuration. Praseodymium similarly, to some extent, sometimes, although I will tell you in a minute about the oxidation states of lanthanides and actinides, the plus 4 oxidation state is very rare. Most common oxidation state for lanthanides is plus 3. For plus 4 oxidation state, it is very rare. So still 5 elements total, it can show to some extent the plus 4 oxidation state, although unstable it will be. Similarly for praseodymium, I can do the same. I can remove another electron. For neodymium also I can remove another electron. Praseodymium, samarium, europium, gadolinium is very stable, so it will not tend to lose its half-fill stability. And dysprosium. These 5 elements to some extent, although our most of the concern will be on cerium plus 4 and terbium plus 4. Cerium plus 4, why? Because it is getting the inert gas configuration, and terbium plus 4, why? Because it is getting the half-filled configuration. Others do not show much of variation in their plus 4 oxidation states. Plus 3 oxidation state, in a minute I will tell you, it is the most common oxidation state for lanthanides. Most common oxidation states for ln n plus. In a much similar manner, just like lanthanide electronic configurations, we also want to investigate the actinide's electronic configurations. Yes, actinides, if you cannot memorize and remember the names and sequence for the time being, okay, fine, no issues. But the similar way I told you for lanthanide series also, if you can at least remember the lanthanides, it is important. And I told you during 11th standard only, Jinia to jodi mone thake, that you in 12th standard have to anyway remember the lanthanides. If not actinides, then still okay, but lanthanides you should and you have to. For actinides, if the electronic configurations will be given, then we will be able to, atomic number is given, then we will be able to take a hint and we will be able to take a quick recap or quick recall that what should be the electronic configuration according to that atomic number. But what if in the question they are asking which of the following is an example of actinide? Let's say you have not memorized or you do not have the knowledge of lanthanide names. Now you don't know lanthanide names, you don't know actinide names. Then how will you be able to tell that dysprosium, in between dysprosium and californium, which one is lanthanide and which one is actinide? There also I am telling you a hint or a trick can be applied. যদি আমি অ্যাক্টিনাইড আর ল্যান্থানাইডের মধ্যে ডিস্টিংগুইশ এক্স্যাক্টলি নাও করতে পারি, অ্যাটলিস্ট যদি আমাকে জাস্ট বলে যে কোনটা অ্যাক্টিনাইড কোনটা ল্যান্থানাইড বলো, দেন ফর অ্যাক্টিনাইডস দ্য নেমস আর মোস্টলি গিভেন বাই দ্য ডিসকভারার অর বাই দ্য প্লেস নেমস. Most of the names are given that way. I will show now. So it is starting from thorium, protoactinium, uranium. Till uranium it is naturally occurring. So it is 92, 91, 90. After uranium, whatever comes, it is artificially made, it is man-made. So after uranium, all the names are after some planet names, after some scientist name, after some place or country name. It is mostly like that. So based on that, you can make a call, okay, these names are not likely to be lanthanides, these names are likely to be actinides. If in the question straightforward they are asking, because you have seen that in column match questions, sometimes they ask these kind of easy questions also, that which of these following you match the column S block, P block, D block, F block, etc. দেখেছি তো আমরা সেগুলো? Correct now? So আমাদের এর পরের যে নেমস গুলো আসবে, they are mostly after these type. So you see Neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, lawrencium. Till lawrencium it is 103. That means starting from 90 to 103, these 14 elements are supposed to be my actinides. And you can see after the name of planets, places, like americium is named after America obviously. Neptunium, plutonium named after planets. Curium is named after Mother Curie. Then californium named after California. Einsteinium named after Einstein. Fermium named after Fermi. Mendelevium named after Mendeleev. Like that the names are being done. So you can make a call that okay, these are supposed to be actinides and all. Clear for all? অর্ক ব্যাপারটা মাথায় ঢোকাতে পেরেছি? যদি নাম মনে নাও রাখতে পারি। So m, similarly m plus 3 and m plus 4. Though here also m plus 3 will be the most stable oxidation state, m plus 4 will be very rare, but we will have a look at these also. Now why 4f and 5f are different, that we will talk. So for these, what are we supposed to do is, before the previous one, for the previous one it was 4f 5d, for these ones it is 6d and 5f. So 5f 6d 7s. Now thorium is such a stupid actinide or F block element that does not have any F electron. Remember this way, the first member itself does not have any F electron. So it is supposed to be, by the way, in all these cases it will be 7s2 7s2 7, just like the previous case 6s2 6s2, it is also 7s2 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 7s2, and this case it is supposed to be 2. No electrons in 5f for thorium. That is the only one among the actinides that does not have any 5f electrons. Now afterwards, if I start moving, I start getting what you see. It is supposed to be 1 and 2, but as we know, the hero of our series is F subshell, so we will always try to increase the exchange energy in the F level. So what we will do is, I will transfer 1 electron in F from 6d up to neptunium. Now plutonium onwards, it says that okay, forget about it, you start giving me all your electrons. That means no, afterwards no electrons in d at all. So it was supposed to be 5-1, it is 6-0 7-0. Now you see, if it is 7-0, half filled gained. So for curium, when it comes, it does not want to break it half filled stability, so that's why it is giving its electron to 6d. Then again from berkelium onwards, it starts taking the electron from 6d. 9-0 10-0 11-0 12-0 13-0 14-0. So 14 done, so it is 14-1. Come again. Okay. Now you see, when you move more closer to the half filled, for example up to neptunium, it is okay, fine. When you come to plutonium, it starts realizing that my half filled stability is close by, nearby. So it says that you forget, if you look at the exchange energy calculation with respect to F subshell, if it is 4, if it is F4, then the corresponding exchange energy, you see, you check, you have just now calculated the the 4 value, it is standing for 6k. The exchange energy over here, it is 6k, but with respect to 5 unpaired electrons, it is going to be 10k. And in case of 6 unpaired electrons, if you take 6 total unpaired electrons, if you take, then 6 into 6 minus 1 by 2k, which makes it 3 into 5 15. So directly jumping from exchange energy of 6k to 15k. So that huge jump in stability motivates plutonium to take the electron from 6d and become 6. Can you follow that? When it is 2, then the corresponding exchange energy is K. If it takes up this one electron from D, it will become 3 electrons in F, and it will give you the corresponding exchange energy value of 3K. So the difference in energy is only 2 unit. এখানে যদি আমার এটা দুটো এনপেয়ার্ড ইলেকট্রন হয় তাহলে তার এক্সচেঞ্জ এনার্জি K হবে. If it takes this extra electron into 5F, then 3 unpaired electrons will be there in 5F. That will give you 3K of exchange energy. It is not a huge motivation to do that shuffling. Can you guys follow? What Orko Prabhu asked is very genuine question. মানে আমার exchange energy jumpটা যদি খুব বড় হয়, it will give me a very good push to take the electron from 6d.
স্যার ওখানে ম্যাক্সিমাম জাম্পটা হচ্ছে মানে 5f4 থেকে 5f6.
Correct. So that is motivating it to take the electron from 6d. Is it clear for everyone?
Yes sir.
Now next is you are supposed to go for the +3 oxidation states. If I have to write the +3 oxidation, +3 directly, if I have to write down, that means for thorium 2 electrons taken from this one, 1 electron taken from this one. So technically it is supposed to be what? 6d1, but this is so stupid. It is not 6d1.
5f1.
Because 5f is more closer to the nucleus. +3 electron +3 charge increases the Z effective to high, making the electronic attraction by the nucleus very much higher. So if the electron is there in 6d versus in 5f, 5 being more closer to nucleus, plus positively 3 charged cation will bring down the electron from 6d to 5f. Are you guys able to follow? That is happening with this stupid thorium. All the problems happens with stupid thorium. But apart from that, if you look at the other ones, it is not so problematic at all. Because if you come to protoactinium, no problem. 5f2, 5f3, 5f4, 5f5, 5f6, 5f7, half fill stability gained, 5f8, f9, f10, f11, f12, f13, f14. Clear for everyone?
থোরিয়ামের গ্রাউন্ড স্টেটে f ইলেকট্রন ছিল না, বাট m3 প্লাসে f ইলেকট্রন আছে.
Let me write it down for you. When thorium +3 gets formed, the electron, the residual electron or the remaining electron should be placed in 6d, but high positively charged thorium +3 exerts high Z effective nuclear charge upon its valence electron and forcefully brings down the 6d electron into 5f. Clear for all? And similarly, the +4 oxidation state values you can write on your own. Now,
স্যার বলছি একটু উপরে
গেলাম।
হ্যাঁ স্যার বলছি যে যেটা আপনি এনপি লিখেছেন হ্যাঁ ওখান থেকে 4-1 থেকে 6-0 হচ্ছে
4-1 মানে আচ্ছা 4-1 থেকে 6 কি 4-4 আচ্ছা হ্যাঁ 4-1 থেকে 6-0 ইয়েস।
হ্যাঁ মানে ওখানে এক্সচেঞ্জ এনার্জি ডিফারেন্সটা 15 - 6-9 আসছে।
দেখো কোথায় গেল এটা, ধরো আমি 4-1 যদি দেখি তাহলে 4 এর এগেইনস্টে দ্য এক্সচেঞ্জ এনার্জি ভ্যালু ইজ 6k and 6 এর এগেইনস্টে এক্সচেঞ্জ এনার্জি উইল বি 15k. So 9 exchange energy gap is 9 units.
কিন্তু যদি আমরা ওটা লাইক 6-0 না করে 5-1 করে 7-0 করে দিতাম
5 আরেকবার কি
5-0 না করে 5-1 করতাম
5-1 করলাম
হ্যাঁ পরেরটা 7-0 করছি তাহলে ওখানে এক্সচেঞ্জ এনার্জি ডিফারেন্সটা বেশি আসে।
No, difference in between 4-1 versus 6-0. Now you are comparing neptunium versus plutonium. Then why are you bringing americium in between? You are looking for the jump in between neptunium or change in between neptunium to plutonium. No, americium is half filled. Okay, that is very much valid reason that it will experience the maximum stability in terms of exchange energy. You are not supposed to get americium into the picture when you are talking in between neptunium and plutonium. যখন আমি neptunium plutonium comparison করছি তাদের exchange energy difference টাকে ভাবছি। If it was 5-0, you can argue on this. If it would have been 5-0, then against that 10k would be the, what is that called, exchange energy. Whereas this is giving me 15k. If I would have made it, now it is 3-1 in uranium. So against 3, the exchange energy is 3k. So from 3k to 10k to 15k, that way you can compare. আবার তাহলে আমাকে এখান থেকে শুরু করতে হয় যে প্রোটোঅ্যাক্টিনিয়ামে 2টো আনপেয়ার্ড ইলেকট্রন আছে, তাহলে আমার এক্সচেঞ্জ এনার্জি কে, 3টে যদি হতো তাহলে এক্সচেঞ্জ এনার্জি হতো আমার 3k, তাহলে k আর 3k এর মধ্যে 2k এর গ্যাপ, that is not giving enough motivation. Like that 3 unpaired electrons giving me 3k. হ্যাঁ
ওটাই বলছি যে প্লুটোনিয়ামের am যদি দেখি ওটা প্লুটোনিয়ামকে যদি 5-1 ই রেখে দিতাম তারপরে am এ যদি 7-0 করতাম ওখানে গ্যাপটা 11k আসতো, ওটা ম্যাক্সিমাম গ্যাপ আসে মানে প্লুটোনিয়াম আর am এর মাঝখানে। এখানে তো 9k আসছে ওই নেপচুনিয়াম আর প্লুটোনিয়ামের মাঝখানে।
15k and 7 into 7 minus 1/2 3 21 11 okay 11 আর এখানে 15 আচ্ছা না, then the motivation for americium to get the half filled is very clear because of half filled. I am looking forward from neptunium to plutonium. You are talking, তুমি ভাবছো যে americium তাহলে আরো বেশি স্টেবিলিটি পেতো প্লুটোনিয়ামের থেকে, না আমার সেটা তো কনসার্ন না, আমার কনসার্ন হচ্ছে প্লুটোনিয়াম নেপচুনিয়ামের থেকে বেশি স্টেবিলিটি পেল বাই ডুইং অ্যাডজাস্টমেন্টস। americium তো প্লুটোনিয়ামের থেকে বেশি স্টেবল, obviously evident in terms of exchange energy, no problem. Even if it is 11 unit of energy gap or 9 unit of energy gap, whatever it is, americium is more stable, no doubt. I am more interested to look into the energy stability, exchange energy stability in between neptunium and plutonium. neptunium থেকে প্লুটোনিয়ামে গেলে আমার স্টেবিলিটিটা অনেকটা বুস্ট আপ হচ্ছে টু বাই মেকিং দ্য শিফট ফ্রম ডি টু এফ। বুঝতে পারছি কি সত্যজিৎকে? সবাই কি এটা বুঝতে পারছো কোয়েশ্চেনটা? ওকে দেন চলো, what is the note? You see, for lanthanides the electrons are getting filled up in 4f subshell majorly, and for actinides the electrons are getting filled up in 5f. Now you guys think and tell me, Orko think and tell me, which orbital is more exposed towards the periphery? বাইরের দিকে exposed কোনটা 4f আর 5f এর মধ্যে? So if 5f orbital is more exposed towards the outer side, chemically more inert will be which one? Lanthanides or actinides?
Lanthanides, 4f.
Correct? No, because 4f orbitals are more deep seated, more tightly held by the nucleus inwards. So lanthanides are comparatively much more reluctant to participate in chemical reactions, whereas actinides, they are not so much reluctant like lanthanides. They can do a lot of chemical reactivity. Can you understand? Let me write it down. Let me write it down. Although the 5f orbitals and 4f orbitals resemble in their angular wave function, because for both of them, as we know, number of angular nodes, the magnetic quantum number, the azimuthal quantum number will be the same, only the principal quantum number different, indifferent. Now because of this different n value, the 4f orbitals are more deep seated towards nucleus. Why is that so, sir? Because of lower principal quantum number. Mosam বুঝতে পারছিস কিনা? मौसम, श्यामाश्री, नेहा, मिश्रो, जिनिया, हाँ হ্যাঁ ওটা মানে অন প্রিন্সিপাল আমরা কোনো +4 এর স্টাডি যদিও বা অ্যাক্টিনাইডস এরও করি না, বাট ল্যান্থানাইডের থেকে অ্যাক্টিনাইডের যেহেতু কেমিক্যাল প্রপার্টির ভ্যারিয়েশনস বেশি, তাই এখানে সবকটাকেই তুমি +4 এর লিখে নিতে পারো। আমি সেটাই বলে দিলাম, ইউ ক্যান গো অ্যান্ড রাইট দ্য +4 অক্সিডেশন স্টেট ফর অল দিস অ্যাক্টিনাইডস বিকজ দে আর মোর কেমিক্যালি অ্যাক্টিভ।
স্যার প্রথমেরটা কি ইনার্ট গ্যাস স্টেট কনফিগারেশন হবে?
একদম 100% it will become 5f0, that means it will get the radon configuration.
Radon.
So coming back, the 4f orbitals are more deep seated towards nucleus than 5f, and that's why the 5f electrons can participate more in bonding than 4f electrons. So actinides have larger variety in oxidation states than lanthanides. যেখানে ল্যান্থানাইডদের মোস্ট স্টেবল অক্সিডেশন স্টেট +3, অ্যাক্টিনাইডসেরও মোস্ট স্টেবল অক্সিডেশন স্টেট +3, বাট অ্যাপার্ট ফ্রম দ্যাট +4 oxidation state for actinides can also be possible. +3 is the most stable oxidation state, and +4 oxidation state is unlikely that in case of actinides +3 oxidation state, still here also most stable, here also +3 oxidation state is the most stable. Besides, +4 oxidation state can also exist. For example, let's say UO2, uranium oxide. It is very much abundant. Uranium is very much found in the form of its oxide form only. UO2 is very common. But that if I talk about any lanthanum compound in its +4 oxidation state, it is unlikely, and that we are going to address now in terms of oxidation number shortly. Are we clear till now? Quickly let me know. সবার ক্লিয়ার আছি? হ্যাঁ বল অর্ক। হয়ে গেছে? আরে আমি if it's done, then let me know. I hope you are able to see the screen on the left. Tell me. Lanthanoid ions with 4f7 configuration are. So you are supposed to know you have to address the electronic configuration. So +7 means clearly most likely while we were writing the configuration for gadolinium, so it was there 4f7 5d1 6s2, so +3, gadolinium +3 will be the 4f7. You guys can check out your own write up also. Here you see gadolinium +3 is being 4f7. And europium +2 is also 4f7, and terbium +4 is 4f7. These three are 4f7. Correct or not? So which options are matching? मौसम ऑप्शन कोणता? जिनिया, मोइत्री, A and B. Correct. Here you see, as I was talking about Orko. Acha Orko, by the way, you have done the noting down, no? Now this particular question I was talking about, what if they are asking that which are lanthanoids or which are not lanthanoids, something like that, then how are we going to take the call? then we can take the call by looking at the names also, even if we do not remember the exact series. Europium, then curium is actinide, correct or not? Curium is what?
Actinide.
How much? How many are there? 3 plus 3, 6 are given. Out of these, you see, EU,
The 3.
3. Which are actinides then? Which do not belong lanthanide. Which are not belonging to lanthanide? Curium does not belong to lanthanide.
RYD.
ER to aerobium. ER is aerobium, that is lanthanide.
Sir, only curium.
Only curium. That is only actinide. Remaining all are lanthanides. You are just not. You cannot. ER is not. Maybe ও একটা ভাবলো যে ইউরোপিয়াম, তাহলে somehow এটা ইউরোপের নামে রাখা অ্যাক্টিনাইড হবে, correct না নেহা? So alone that concept is not going to help you. You have to know it. Okay, do this one. But diamagnetic means no unpaired electrons. So cerium plus 4 to hobe, because cerium plus 4 is inert gas configuration, that is for sure. And lanthanum, what is the electronic configuration for lanthanum? Just now we have done in the beginning for the D block elements. It is same as scandium, yttrium, lanthanum. That means D-te একটা and S-এ দুটো, 3 unpaired, 3 total electrons. So lanthanum plus 3 and cerium plus 4. But they are talking about diamagnetic lanthanoid ions. Now I'm leaving it up to you. Tell me. Neodymium plus 3 and cerium plus 4. Neodymium. Do you feel neodymium plus 3 will have 0 unpaired electron?
Sir, option B হবে.
Okay.
Option B.
Okay.
Option B হবে মনে হয়।
Okay. তুমি তো করেছো, তোমার খাতায় দেখো না, এখন তো করলে। You have just now solved this particular thing.
ওই দুটো ডায়াম্যাগনেটিক আর অন্যগুলো তো প্যারাম্যাগনেটিক আছে।
The remaining ones have at least 1 unpaired electron for sure. Neodymium, if you look at it, cerium, praseodymium, neodymium. So neodymium will have at least 6 electrons, including F, D and S. So 6 electron থেকে 3 minus করে দিই যদি, তাহলে at least 3 electrons still will be left. How is it diamagnetic then? Now in order to solve these questions, what you are supposed to do? You are supposed to write down the electronic configurations. Without that you cannot do it. Can you follow?
Sir. Lanthanoids polish.
Correct. Because others are not matching. That's why I have to take that call.
স্যার অপশন ডিটা তো ম্যাচ করছিল।
অপশন ডি কিভাবে ম্যাচ করছিল? lutetium plus 3, that is correct, but europium plus 3 unpaired electrons তো আছে europium plus 3 তে। lutetium
প্লাস 3 4x 6 তো।
হ্যাঁ, 6 এ তো 6টা unpaired electron হবে।
ও হ্যাঁ,
তুই পি এর রেসপেক্টে কেন ভাবছিস? পি তে 6টা মানে আমার 0 unpaired electron, বাট এফ এ 6টা ইলেকট্রন মানে 6টা unpaired electron। P তে 6 মানে 0 আনপেড, বাট F এ 6টা মানে তো 6টা আনপেড। Tell again, Orko, which of the following elements have half-filled f orbitals in their ground state? Again, you have to draw the, as I told you, most likely they will give you the electronic configurations, but you have to know the patterns. Like one thing I have told for a shortcut, that gadolinium 100% it is going to be F7, and before gadolinium is going to come which one? Samarium. Europium will come before gadolinium, that will also have the F7. You check out your options, I mean solving. As I told you that for lanthanide elements, cerium, gadolinium and lutetium, these three elements will have electrons in their d subshell, where in lutetium 14 electrons will be there in F, for gadolinium 7 electrons will be there in F. If for gadolinium there are 7 electrons in F, 1 electron in D, then definitely europium will also have 7 electrons in F. Everyone couldn't understand that?
Understood, sir.
So most, maybe it is ABCD I have to consider. They have not cleared this. It's so B and C. So technically, it is very much confusing. What is ABCD? They have not clarified. Maybe. Then europium and gadolinium should be coming in B and C. Is a B and D, no? 1 2 3 B and D तो ऑप्शन ही नहीं, अच्छा B and D अच्छा, correct. Tell me, neodymium plus 2. Neodymium plus 2.
Option
अच्छा, so like that we can continue. The F orbitals are half and completely filled respectively in lanthanide ions, where it will be half filled and where it will be fully filled. So that we have to take the calls. All are lanthanides given here. Europium, then it is thulium, samarium, dysprosium, ytterbium. 4 elements are given. Now you have to do the electronic configurations accordingly that we have just now practiced. Can you guys follow? I mean, proper atomic number লিখে নিতে পারি. It is also given. Europium plus 2, and there it is coming thulium plus 2. Thulium plus 2, how is it fully filled? First one has to be half filled, second one has to be fully filled.
Option C.
Sir, option C হবে।
লুটেশিয়াম একদম তলায় আসছে, half filled and completely filled respectively. Then how is it matching respectively? Because if you are putting it option C হচ্ছে,
এটা তো পুরোটাই মানে হাফ ফুল নট ফুল। স্যার সি হবে, কারণ এখানে TB2 প্লাস তো 0.9 আর আরো তো বেরিয়ে তো হাফ ফিল হবে
না। TB plus 4, TB means what is it? TB we are getting terbium plus 3 means half filled, yes, and ytterbium plus 2 te correct, C হবে. Is that clear for everybody?
Yes, sir, yes.
সবাই বুঝতে পেরেছিস? অর্চিতা, ডেকা,
হ্যাঁ,
সমন্ত, চলো।
হ্যাঁ স্যার।
Now, next part is atomic and ionic radii. Now, for this particular part, I am asking you guys to refer the 11th periodic classification. Refer 11th periodic table. We have discussed over there lanthanide contractions, down the group 3d to 4d size increases, 4d to 5d due to lanthanide contraction size remains almost constant. In the 5d series from left to right, due to lanthanide contraction, size starts decreasing drastically. This is called lanthanide contraction due to the poor shielding effect of F subshell. We have discussed all those things in 11th. Can you follow that? Vishik?
Yes, sir.
You have to refer that particular part. Now we are coming to this part of enthalpy of atomization, melting point, density. For D and D block elements typically. For transition elements. Now you see, before we get into the deeper part of this particular context, let us try to understand that what is the logic behind metallic bonding. In metals, because we know in transition elements all are metals, correct or not? Hard metals. In metals, as we know, there are free electrons available into which the atomic ions float thus the electrostatic force of attraction between those two is the origin of strong metallic bonding. Now this metallic bonding will get further stronger if the number of unpaired electrons are more. Correct or not, guys? Tell me, its strength will be dependent. Its strength क्या है? Its strength will be dependent on what? Strength is directly proportional to what? Number of unpaired electrons in the ground atomic state. Greater is the number of unpaired electrons, higher will be the strength of metallic bonding, and higher is the strength of metallic bonding, we should expect higher enthalpy of atomization. Because if you guys recall, what is enthalpy of atomization? Definition of enthalpy of atomization, what is that? Try to recall. Spandan, what is the definition? The amount of energy required to convert 1 mole of any combined state into gaseous atomic state. That means 1 mole Fe solid, if I wish to convert that into 1 mole Fe gas, then the amount of energy that will be absorbed, that is known as delta H atomization. Sir, isn't that enthalpy of sublimation? Yes, for metals both are the same things. Similar to enthalpy of what is that called, sublimation. For metals, enthalpy of atomization and enthalpy of sublimation both are the same things. Now, when do we expect enthalpy of atomization to be higher? If the strength of metallic bonding is strong, then the enthalpy of atomization should be what? Tell me. Correct, no? So enthalpy of atomization should be proportional to strength of metallic bonding. Shamasri, can you follow? বুঝতে পারছিস কি পারছিস না? Strength of metallic bonding. Rinjin, Jinia, which usually increases with increase in the number of unpaired electrons. যত unpaired electrons এর নাম্বার বাড়বে তত আমার strength of metallic bonding increase করবে, ততই আমার enthalpy of atomization ও increase করবে. Can you guys follow? Now if that is true, then you see, if I look at the electronic configurations which we discussed in the very beginning, then you will find that here the if I'm moving like this way, scandium to titanium to vanadium to chromium, you see 1 unpaired electron, 2 unpaired electrons, 3 unpaired electrons, 6 unpaired electrons in chromium. Then afterwards, if I further carry forward this particular trend, then pairing is started. Then number of unpaired electrons again started dropping. It is from 6 it became 5, then it became 4, 3, 2, 1, 0. For zinc, cadmium, mercury, basically there are 0 unpaired electrons present. Can you follow?
Yes, sir.
So as a result of which, what is happening is we can expect that that enthalpy of atomization up to the mid of the series, more or less, will keep on increasing, then afterwards it will keep on decreasing. Can you follow, everyone?
Yes, sir.
Similarly, the melting point also to some extent is related to enthalpy of atomization. যার enthalpy of atomization বেশি, তার স্ট্রেংথটাও বেশি, তাহলে মেল্টিং পয়েন্টটাও বেশি হবে। Now melting point have got a little bit more things to do, like in the metallic lattice, how effective is the lattice binding, the lattice structure, how strong is that. Apart from the number of unpaired electrons, the lattice binding is also very much important, but that lattice binding patterns and all is beyond our scope of understanding, because solid state we don't know, and we have no opportunity to study solid state right now. So melting point and enthalpy of atomization more or less follow the similar trends, but it will be giving me a bit of up and down in some places. For instance, if you look at it, if I am going down the group, pay attention, what is happening to the surface area of the metals? Increasing. So if that increases, then what do you expect to happen to the extent of attractive forces? So what do you expect to the melting point the enthalpy of atomization down the group? It will increase. Everybody agree with this or not?
Yes, sir.
No.
Yes, sir. Please.
No. When we move left to right across the period, the number of unpaired electrons first increases up to more or less midpoint of the series, and then pairing of electrons start and number of unpaired electrons decreases. Do we agree? Thus, strength of metallic bonding first increases up to midpoint and then starts decreasing. Hence, melting point and enthalpy of atomization also show similar trends. Tell me guys, have you understood this part or not? Come on. Everyone? Pranjal, Moitri, Shawarika, everyone
Yes,
else?
sir.
Also clear now? Now,
Yes, sir.
down the group, Lata understood?
Yes, sir.
Down the group as we move, the surface area of the atoms increases, which causes better, or rather I should say stronger force of attraction. Shamashri, Jinia, Neha, Maria, Shivangi, Rinjim, Mishra, বুঝতে পারছিস কি পারছিস না?
Yes, sir. Yes, sir.
Which causes stronger force of attraction, and thus melting point or delta H atomization down the group increases. Now take out your NCERT everyone. Part 1 NCERT class 12, everybody go and collect, come on quick, and open D and F block elements. Opened?
Yes, sir.
So from there come to this part of, in the very beginning you will find it under the physical properties segment only, in the beginning of this chapter itself. So I will be trying to portray this one. So now you see both the graphs side by side. The first graph, if you can understand, it is the first one. It is the melting point graph. It is the delta H atomization graph. So can you understand similarity in both these two graphs? Here you will find in your textbooks that green color is denoting the first transition series, that is, this one is standing for the 3D series, this one is for 4D series, this one is for 5D series. As you can better understand from the melting point variation graphs also, this is titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. They have omitted showing this for in this instance. Similarly, you can see zirconium, niobium, molybdenum, technetium, ruthenium. This is standing for the 4D series, and afterwards hafnium, tantalum, tungsten, etc. Now you see left to right, somewhere at the midpoint, the melting point is supposed to be maximum because of maximum number of unpaired electrons. Can you follow? Tell me, come on, quickly. Somewhere in the midpoint we are supposed to expect the maximum melting point because of greater number of what is that called, unpaired electrons. Can you follow?
Yes, sir.
So every time more or less here melting point at chromium level, it is getting at peak. Chromium, molybdenum, tungsten, they're in the same group. That's why you see now again down the group, just now we discussed what is it happening, melting point increasing. Tungsten, that is the reason it is the highest melting point metal and used as a filament. Can you follow that?
Yes, sir.
It has got very high melting point. So what are the important takeaways from melting point?
Correct. I take over here. Hopefully not that.
So first takeaway, if I look at from the graph, you see titanium to vanadium to chromium, it was gradually increasing, but then when in manganese or when in technetium the pairing started, all of a sudden there is a sudden dip. Can you see that? All of a sudden there is a certain dip from chromium to manganese or from molybdenum to technetium because of sudden sudden pairing started. Suddenly the pairing of electrons started. Are you able to follow that?
Yes, sir.
But then from tungsten to rhenium there was no sudden dip. Why is that so? Because just now in the electronic configuration we have discussed, you go and see in the very beginning that in the 5D series the anomalous electronic configuration only is present in the platinum. The other ones are not showing any anomalous electronic configurations. That is the reason you will find that for the 5D series, obviously from hafnium to tungsten, because of number of unpaired electrons are increasing, the melting point has increased. Afterwards it has started decreasing. But unlike the case of manganese, technetium, rhenium, they are in the same group. But as we can see in the 3D and 4D series, manganese have shown a sudden dip followed by again a little bit increase. Technetium again shown a sudden dip from molybdenum followed by again a little increase, but that we are not seeing in tungsten to rhenium. I mean tungsten to rhenium to osmium to iridium gradually decreasing because number of unpaired electrons gradually decreasing. So the first takeaway is in the 3D series from what is that called, manganese, what is the electronic configuration? I'm sorry, chromium, what is the electronic configuration, everyone? Just now we have experienced 3D5 4s1. To manganese, what is the electronic configuration in manganese?
3 5 4s2.
So all of a sudden the number of unpaired electrons decreased. So it took some time to adjust with that unfavorable change. Oh my god, what happened? Why all of a sudden this number of unpaired electrons got decreased so much? That's why a sudden dip in the melting point we are experiencing as we are moving from chromium to manganese. And the similar kind of anomaly, so in 3D series from chromium to manganese, and in the 4D series from just below chromium it is molybdenum, and just below manganese it is technetium. So for molybdenum, what is the electronic configuration? Just now we have experienced that.
45
Very good. Then that we are going to technetium. What did we experience? Orko was claiming something also. It is 46 5s1. Correct now everyone? কোনটা? ইলেকট্রনিক কনফিগারেশন তো অলরেডি করেছি, আবার কি বলবো? শুরুতেই তো করলাম, এখানে আমি আবার কি বলবো? একদম শুরুতেই তো we have discussed all the electronic configurations in details. That only I am writing once again. Shamashri, Maria, অন্বেষা, জিনিয়া, এটাই তো করলাম একদম শুরুতে, তো এটাই ইলেকট্রনিক কনফিগারেশন শিখে নিলাম. So in the 3D series from chromium to manganese, and in the 4D series from molybdenum to technetium, there is a sudden decrease in the number of unpaired electrons, and that is why there is a sudden dip in melting point from chromium to manganese or molybdenum to technetium. But if I look at that for tungsten, as we just now told in the beginning, that tungsten is not having a similar configuration with molybdenum. It is showing very much simple, straightforward configuration. 5D, and as it is supposed to be, it is doing that way. 5D3, 6s2, and rhenium also 5d4. I think it was 5d4 only. Correct or not? Just check it out once again.
আপনি একবার টিসি ইলেকট্রনিক কনফিগারেশনটা চেক করুন না।
টিসি ঠিক আছে, ওটাই আমি যেটা বলে দিয়েছি, আজকে বলে দিয়েছি, which I have told today. That is the electronic configuration.
স্যার একটু নিচে যাবেন।
Just a minute. It is supposed to be, I'm sorry, it is 4 to 6-2, yes. If I have mentioned something otherwise in 11th Orko Provo or in anyone else note for technetium electronic configuration, please make a correction. The configuration that I have written today, that is the actual configuration for technetium. Maybe out of some flow we have done that wrongly in the previous time. You make a correction of that. Okay, Orko? Quickly let me know, come on fast. Come on fast.
এই নোটসটাতে আগে আপনি কি লিখেছিলেন এটা ইলেকট্রনিক কনফিগারেশনটা?
হ্যাঁ, কাম এগেইন।
মানে এই যে নোটসটা লিখছেন এখানে টেকনিশিয়ানের ইলেকট্রনিক কনফিগারেশনটা কি লিখেছিলেন আগে?
এই তো
ঠিক আছে স্যার, আমাদের নোটসে অন্যটা লেখা।
কি লিখলাম আমি? মানে তোর নোটসে কি লেখা আছে?
4:5:2।
হ্যাঁ, সেটাই বলছি, যদি কিছু অন্য লিখিয়ে থাকি আগে, দেন মেক আ কারেকশন অফ দ্যাট অ্যাকর্ডিংলি। এ আর এক ছাগল আমার, এ আবার গুগল খুলে বসে আছে আমার অর্ক। তুই গুগল দেখে নিটের পরীক্ষায় বসবি? Clear for everyone? অর্ক,
হ্যাঁ নোটসটা দেখা নোট
please do it fast. No, melting point order they will not ask on anyone, because it is very much abrupt and anomalous. Order exactly I will not be able to produce. What we will be able to produce is that I am writing out of summary that 3D, 4D, 5D maximum melting point and minimum melting point maximum for 3D series obviously in the mid junction only chromium, and followed by chromium, bottom of chromium is chromium, molybdenum, tungsten, and minimum for every cases is the last member where 0 unpaired electrons are there, zinc, cadmium, mercury with 0 unpaired electrons. I will not be able to arrange in the melting point order because it is too much of anomalous pair. Now if I want to come with the what is that called, enthalpy of atomization, in that regard if we want to do the argument in the 3D series alone,
স্যার ওইটা যদি কমপ্লিট করি তাহলে
tell
টাংস্টেনে একটা স্টার্ট করছে না কেন?
টাংস্টেনে কি হচ্ছে?
একটা স্টার্ট হচ্ছে না
মানে কি হচ্ছে না কেন?
যে কোর্স মানে কমছে যে গ্রাফটা
হ্যাঁ
এটাতে স্টার্ট হচ্ছে না, যেগুলো স্ট্যাটিক যেগুলো হচ্ছে না সেকেন্ড থার্ড সিরিজের জন্য,
কারণ because in 5D there is not the in the ground state the electronic configuration is not much anomalous. In 3D and 4D only due to that exchange energy cause or exchange energy phenomena, the electronic configuration anomaly is maximum in the 3D and 4D series only, not in the 5D series. If you look at in the 5D series, only platinum has the exceptional configuration. Platinum followed by gold have the exceptional configuration. The remaining ones are showing the exact same configuration as I would have expected from the Hans multiplicity law or Bohr principle. In the 4D series, maximum anomalous pairs are observed, that due to that exchange energy phenomena. In 3D, chromium and copper is only there, but in 5D there is almost no exceptional pair unless in the end part of the series, in platinum and gold only. বুঝতে পারলাম কি পারলাম না? দেখে নাও। Because you see now Barchi in the sense, because in technetium or in manganese it was all of a sudden the drop in the number of unpaired electrons, so that is the reason it drastically fell down, all of a sudden fell down. But then again, but then it is not like that iron or ruthenium is getting higher value of melting point over molybdenum or chromium. They are still having lesser value only. Just can you hear me? Hello? I think I lost. Just a minute. I think it's showing I lost connection. Okay, just a minute. Because in my laptop I am recording, তো ওটাতে আমার কানেকশনটা চলে গেছে। আরে wait a minute. হ্যাঁ, so it is like অর্ক যে ওখানে আমার কি হচ্ছে যে টেকনিশিয়াম বলো বা ম্যাঙ্গানিজে বলো all of a sudden drop হয়ে গেছে, number of unpaired electrons এর distribution change হয়ে গেছে, for that reason it is all of a sudden showing a drop. But then when I am going for the 5D series, then the number of unpaired electrons variation is not so anomalous. It is not so anomalous in the number of unpaired electrons variations. Like hafnium, if I look at the configurations, hafnium it is 2-2, 3-2, 4-2, 5-2, 6-2, 7-2 as it is supposed to be. Normal trend it is following. So lanthanum, if I exclude 2 unpaired electrons, 3 unpaired electrons, 4 unpaired electrons, 5 unpaired electrons, and so on, it is going on. Orko, can you follow? So it is not. Exactly, correct. Because now you have correct. I understood. Now he is asking that W has the highest melting point as of quoted, but number of unpaired electrons in rhenium is 5, which is more than W. So unpaired electron, if it is the only basis, then rhenium should be the maximum melting point. But that is the catch, that number of electrons is not the only catch. What is that? Number of unpaired electron is not the only factor. What else is the factor? Lattice packing. There are two things that collectively give me the outcome of the melting point and enthalpy of atomization. Lattice packing is also an important factor which is highly in favor for tungsten. Tungsten have got very nice lattice packing. So you can write it here. Again and again I'm getting logged out. We can write it here. Tungsten has very good lattice packing, which makes its melting point and enthalpy of atomization highest. Not only the number of unpaired electrons. So number of unpaired electrons is one factor. Also I should incorporate, as I told in the beginning, that lattice packing efficiency. These two parameters collectively control the melting point and enthalpy of atomization parameters. Can you follow?
গ্রাফটা একবার
ধরতে কি তুই নিজের নিজের বইতেই খোল না, বারবার আমার গ্রাফ দেখাও, এগোবো না নাকি? হ্যাঁ হ্যাঁ হ্যাঁ, কোনটা কোনটা বল। আচ্ছা দাঁড়া, আবে ও একটা থেকে দুটো অব্দি ব্রেক আছে, আর কত এক্সটেন্ড করবো? Look at here. Samadrita, can you follow?
Yes, sir.
আচ্ছা স্যার, বলছি এই যে লাস্টের যে দুটো দেখেছে সেখানে মলিকুলার পিসিআর ডব্লিউ2 CR2 ওখানে ওই ল্যাটিস্প্যাস্টিকের গল্পটা নেই বলে 5 এর পর 6 হতেই সাডেন ড্রপ করছে।
হ্যাঁ এই দেখ, আমাদের এটা সিলেবাস থেকে এক্সক্লুড হয়ে গেছে বলে আমি এই কথাটা বলতে পারছি না। স্ট্রাকচারস অফ ট্রানজিশন মেটালস, that is their solid state structures. HCP means hexagonal closed packing. Earlier it was there in the syllabus, now it is excluded. Titanium can also have BCC. It is not basic concepts of chemistry. BCC means body centered cube. CCP, that means cubic close packing. So like that when we are talking about tungsten, BCC, body centered cubic packing gives its very much highly efficient packing pattern, which overall collectively number of unpaired electrons as well as lattice packing pattern, collectively it provides the maximum stability in its lattice structure. Now this chart earlier we used to discuss, but now because solid state is excluded from the syllabus, we are not supposed to understand about these terms. Can you follow that, Orko? Clear for all?
Yes sir.
Next you see, if I look at the enthalpy of atomization values, then we have to, one thing that got eliminated, the corresponding elements: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. We refer zinc, cadmium, mercury to be volatile metals because owing to the very low enthalpy of atomization. Zinc, cadmium, mercury having very low enthalpy of atomization value are volatile metals. It's not like that, oh, if I keep zinc it will be evaporated, but the extent of transferring into the vapor phase, that is sublimation, will be much more for zinc as compared to the others, and it will be minimum as we compare for vanadium. That means it is minimum volatility, it has got minimum volatility. Can you follow everyone? That is maximum enthalpy of atomization. Delta H atomization is maximum. Now again, Orko, you can think or you can ask, or everybody should think that, sir, vanadium, as compared to vanadium, chromium has greater number of unpaired electrons. Vanadium has got, if I look at the electronic configuration, refer the electronic configuration everyone, vanadium has got 3 unpaired electrons, whereas chromium has got 5 unpaired electrons, 6 unpaired electrons. But then again, unpaired electrons alone do not decide the enthalpy of atomization or melting point. Collectively, the lattice packing as well as number of unpaired electrons decide the overall enthalpy of atomization and melting point. So, come again. Now BCC also have some other features also, their radius ratio, etc. We are not going to get into those technical terms, but yes, we can tell in a brief manner that overall factor is favorable for vanadium when it comes to atomization enthalpy and making it the highest. We just have to remember zinc is the lowest, vanadium is the highest, chromium is the second highest. That's it. Clear for all? Everyone?
Yes, sir. Yeah.
Now it comes ionization enthalpy. Now we will go for a break, but before we go for a break, I'm putting an exercise for you. If you find time, then good, you can do it. You can open your NCERT, you will find it in table number 4. We are going to develop the idea of SRP, standard reduction potential, from here. What are these values, sir? This is the first ionization enthalpy, second ionization enthalpy, hydration enthalpy, atomization enthalpy. Now what is the thing we are talking and arguing on? Let's say, what are the process? We are going to develop the Born-Haber cycle. M, it was solid. If I apply enthalpy of atomization, I will get what? M gas. If I want to achieve M plus gas, I have to apply what? First ionization enthalpy. If I have to get the second positively charged, second ionization enthalpy, M plus 2 gas. That if I want to convert into M plus 2 aqueous, what will it release? Hydration enthalpy, correct everyone? Tell me everyone. Shamastri, Jaya, thermochemistry. Hydration enthalpy. Now, so according to Born-Haber cycle, if I directly wants to go from here to here, that means M solid to M plus 2 aqueous, if I want to go, then what will be the delta H total? Tell me everyone. This plus this plus this plus this, correct or not everybody? Because enthalpy is a state function, I can just simply add them up, correct everyone?
Yes, sir. Yes, sir.
So now my let's say I am taking copper for example. Copper solid, to copper plus 2 aqueous. If I want to convert this phenomena, or if I want to carry out this particular process, then what am I supposed to get the delta H total? 330. This is the atomization enthalpy, first ionization enthalpy, second ionization enthalpy, hydration enthalpy. So in the sequence I am adding them up. 339, because obviously enthalpy of atomization is endothermic, I have to provide the energy. Enthalpy of ionization, I have to provide energy, endothermic. Enthalpy of second ionization enthalpy, also I have to provide energy. But hydration enthalpy is what? If the ion is dissolved in water, it is supposed to produce energy, or am I supposed to provide energy?
Sir, it will produce energy.
It will produce energy, then only it will get stability. So that's why you see that is exothermic. So I'm adding them up. 745, 1958 minus 2121. I'm taking the help of the calculator for the moment. Just a minute. So 339 plus 745 plus 1958 minus 2121. So 921 is the corrective value. That means you guys think and tell me that in order to convert solid copper into aqueous copper plus 2, it is endothermic or exothermic, that means.
Endothermic.
So it is thermodynamically favorable. Is it thermodynamically favorable or unfavorable?
Unfavorable.
So in the other way, that is copper plus 2 copper will be favorable or unfavorable?
Favorable.
Okay, so if I try to recall, assuming delta S for the process, although it is definitely not 0, but I'm just assuming approximately to be 0, delta G will be how much? Let's say delta G naught I'm just considering, because all these are standard enthalpy values. If you look at it, these all are standard enthalpy values. So delta G will be delta H naught minus T delta S naught. This value approximately I'm assuming to be 0. So that means delta G naught is supposed to be approximately plus 921 kilojoules per mole. Am I right or wrong, everybody? Quickly tell me.
Delta G naught.
Delta G naught. Now according to Nernst equation, what can we do? Delta G naught is equals to minus NF E naught. Now delta G naught is coming what? It is plus 921 into 10 to the power 3 kilojoules per mole. Am I right or wrong, guys? Everybody? What is the value of N? 2, right? Hello, come on.
Yes, sir.
Correct me?
Yes, sir.
And F 96,500 approximately 96,500 coulomb per mole. E naught I don't know, I have to calculate. So these things are getting cancelled. By the way, this is joules only. Now coulomb, here it is coulomb and here it is joules. So coulomb and joules, if I calculate, it will come in volt. If I cancel joule by coulomb, it will give me what? Volt only, correct or not? Negative sign is there, yes. So it is giving me how much? 921 multiplied by 1000 divided by 2 multiplied 96,500. Tell me, correct or not? Everyone, come on.
Yes, sir.
So 921 divided by 2 divided by 965 multiplied by 10 is somewhere approximately, it is somewhere I did mistake, I guess. সব জায়গায় ক্যালকুলেশনস গুলো ঠিক আছে, দেখে নাও তো একবার কুইকলি। ক্যালকুলেশনস গুলো কুইকলি একবার চেক করো তাড়াতাড়ি। আমরা একটা ব্রেক নেবো তারপরে। একটু তাড়াতাড়ি চেক করো ক্যালকুলেশনস গুলোকে। হ্যালো,
হ্যাঁ স্যার,
চেক করো, চেক
ঠিকই
করো।
আছে।
745, 339, 90, 921 is only coming, all these values are in kilojoules per mole. So it is multiplied by 1000, it has to be divided by 2, that has to be divided by 96,500, 4.77. Something wrong is happening. Some decimal value change is happening somewhere. Acha, okay, right, okay. So E naught is coming out to be approximately how much? Minus 4.77 volt. Clear? This is for what? Copper to copper 2 plus, copper solid to copper 2 plus aqueous. But that we have assumed by assuming delta S to be 0, but which is not true, right? Delta S naught cannot be 0. Am I making sense to all of you?
Yes sir.
কারণ সলিড থেকে অ্যাকুয়াস ফেজে গেলে এনট্রপি তো বাড়বে, কিছুটা তো চেঞ্জ হবেই। বিসাইডস টি এর একটা ভ্যালু আছে 298 কেলভিন। আই ওয়াজ নট অ্যাওয়্যার যে কতটা হচ্ছে আমার টি এর ভ্যালু বা কতটা হচ্ছে ডেল্টা ইজ নট এর ভ্যালু, দ্যাটস ওয়াই আই অ্যাজিউম দ্যাট ইট ইজ 0, but technically delta G naught value will be a little bit lesser than this actual value. And if I do that, if I could have done that adjustment accordingly, I should have got E naught copper 2 plus copper. In reality we should get positive, because E naught copper 2 plus, that is SOP. This is SOP, standard oxidation potential. If SOP is coming to be negative, SRP has to be positive. Can you understand, everyone?
Yes sir.
Now that we are not going to fall out to the exact values. We are not going to calculate the exact values, because delta S values are not given to us in the NCERT context. But what we are going to evaluate right now is, in the next class, is that how does the M plus 2M SRP values for transition metals vary if the atomization enthalpy, ionization enthalpy changes in a certain ways. How are we going to address the SRP values? That we are going to address in the next class after understanding the ionization enthalpy. Clear for all, I guess?
Yes, sir.
তো এটা তোমাদের বইতেও চারটা দেওয়া রয়েছে। if you get time please do it. Titanium to zinc, all the values are given. If you find time before our next class, then try to do on your own. If you can solve it, you just try to develop the E naught values, SRP E naught values for the corresponding pairs, so that it will be giving you an idea that what we are going to talk and discuss in the next class. আচ্ছা, তাই তো, হ্যাঁ
নোটসটা পাঠাবেন?
পাঠাবো, এখনই পাঠিয়ে দিচ্ছি। বাট ইয়েস, রিমেম্বার যে আমরা এই লিঙ্কটাতেই আরেকবার জয়েন করব, ঠিক আছে? বাট 2 PM এর কাছাকাছি জয়েন করব, বাট স্টিল আমি যখন একটা কনফার্মেশন দেব তখনই সবাই জয়েন করো।
লাস্ট যেটা করলেন কপার টু প্লাস ওইটা পাঠাবেন।
ঠিক আছে, চলো।